All right, the Tolman-Stewart experiment was critical, and it's important for you guys to understand what's happening there. Let's say we have a conductor, and we have electrons in this conductor, and let's say we shift this conductor over to one side. Tolman and Stewart thought that if charge carriers in metals were negative electrons, they would be free to move, and positive charges would be fixed. Therefore, this experiment, they came up with this experiment to test that. Essentially, that these electrons have inertia and they're going to lag behind. And we're looking at 1916. J.J. Thomson discovered the electron in 1897. So let's take a look at a visual of that. We pull it over and you could see how the electrons lag behind. We rapid acceleration to the right. And those electrons stay back because of their inertia. And so it proved that the charge carriers, what was carrying the charge in metals was actually electrons. And the electrons stay back, making one side more negatively charged, and that proved that theory, and they could see that. Now, it turns out that Ben Franklin in 1747, this is earlier, this is before they knew about electrons and protons and whatever, they designated, or Franklin designated what was positive, what was negatively charged. And he, basically had a 50-50 shot at, describing what was happening. There is a, he said that glass, for instance, like a glass rod like this, if you apply friction on it, it had an excess of fire. But then if you had, let's say like a comb made of, resin or something, or a balloon, they didn't have balloons, but if, equivalent to a comb in terms of what happens, this just has a lack of fire. So they knew about the two different kinds of static electricity. They just didn't have the words to describe what was going on. But he went ahead and assigned, what was positive, what was negative. And if you notice right here, this is actually, the logic's actually backwards, right? The comb really has an excess of fire, or electrons. And then the glass actually has a lack of electrons, making it, a lack of fire, if you want to call fire, the electrons. And so you had a 50-50 shot. Got it backwards, and we didn't find out until much later about what's going on with the electrons, but what's going on, what's actually the charge carriers. And by that time, they already had so many electrical diagrams, everything was set up backwards, and everything worked that way that we've kept it that way. So we'll talk more about that when we get into circuits. When we talk about charge, it's quantized, meaning we can count it, we can, quantify it, we can get a certain amount of it. The smallest possible stable charge is E. That's the elementary charge, is the charge of one electron or one proton. One proton has a charge of positive E, an electron has a charge of negative E, and E is the elementary charge. And the elementary charge is 1.602 times 10 to the negative 19th coulombs. We're going to talk about, how we get the coulomb later. But you can tell here, this is a very, very tiny amount, 10 to the negative 19th. Very, very small amount of charge, and it should be, for an electron or a proton. And the coulomb is the SI unit of charge. All right, so for this one, we're going to take a look at it. Certain static discharge delivers negative 0.5 coulombs of electrical charge. How many electrons are in this discharge? And so if you look on your data booklet, you're going to have the charge of an electron. I went ahead and put it up here anyway. But let's see if you can use logic to figure this out. This really doesn't require an equation. You should be able to figure out this with logic. And so go ahead and pause the clip and give your best shot with that. And then when you're ready to check, you can hit play to continue. Okay, so the total amount of charge is 0.5 coulombs. The elementary charge is negative 1.602 times negative 19th coulombs. And we want to find out how many there are. And so we take the 0.5 divided by the elementary charge, and that's how many electrons we have. 3.121 times 10 to the negative 10 to the positive 18th electrons. It takes a lot of electrons to get 0.5 coulombs of charge. And 0.5 coulombs of charge is a lot of charge. If you think about like a lightning strike on a range of, what is it, 4 to 11 coulombs, that's a pretty decent way there to 4 coulombs. And so this would be a lot of electrons. Okay, so next we want to figure out how much positive charge resides in 3 moles of hydrogen gas, H2. So, and we've got the, Avogadro's constant here. Let's see how you do with this. This would be a good review for you as you consider this. Now, you can do 2 and 3 as well. How much negative charge is there, and then what is the net charge. So go ahead and pause the clip and give it your best shot with that, and when you're ready to check, you can hit play to continue. Okay, so if we have 3 moles, every one of those moles, right? So here's a mole, here's a mole, here's a mole. Inside there are many, 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 many H2s, right? And we know exactly how many there are. We know it's this many, 6.02 times 10 to the 23rd molecules. And so in every single one of those moles, we have that many molecules. And so this is how many molecules that we have. And every molecule, H2, right, has 2 protons, 2 electrons. And, the elementary charge is this. And so this is the total amount of charge. That's the total negative amount of charge. And then what is the net charge? Well, if it's neutral, then, each atom has the same number of protons as it does neutrons, so the net charge is 0.